So picking up with part 4, number 10, a particle moves on a rotating platform. Derive the equations of motion, including centrifugal force, Coriolis force, Euler force, and the trajectory for constant angular velocity. So this is motion in a rotating frame. So in a rotating frame, our A sub inertial equals A sub ROT plus 2 omega plus V sub ROT plus omega cross with omega cross R plus omega dot cross R. So therefore, Newton's second law in the rotating frame, this is going to be M A sub ROT equals F minus 2M omega, and then cross V sub ROT minus M omega crossed with the cross product of omega cross R minus M omega dot XR. So our fictitious forces are going to be F sub COR equals negative 2M omega cross with V sub ROT. F sub CENT equals negative M omega cross with the cross product of omega and R. And F sub Euler is equal to negative M omega dot crossed with R. And for constant omega, that equals omega Z hat and no real horizontal force. So x double dot minus 2 omega y dot minus omega squared x equals 0. And y double dot plus 2 omega x dot minus omega squared y equals 0. And what these do is these describe the inertial straight line motion as seen in a rotating coordinate system. So that's number 10. Now moving on to number 11. So number 11, we have a solid cylinder rolls down an incline whose angle varies according to theta of x equals theta naught plus alpha x. We want to determine the translational acceleration, the angular acceleration, and the speed as a function of distance, and also the normal force. So this is a rolling without slipping problem. So for a solid cylinder, I equals 1/2 mr squared. And a rolling condition is A equals R alpha. And from here along the incline locally, mg sine theta minus f equals ma. And our torque, Fr equals I alpha equals I times A over R. And F equals 1 over R squared times A, and that equals 1/2 ma. So mg sine theta minus 1/2 ma, that's going to equal ma. And A equals 2/3 g sine theta. And since theta of x equals theta naught plus alpha x, A of x equals 2/3 g sine of theta sub theta naught plus alpha x. And our angular acceleration, alpha sub ROT equals A over R equals 2g over 3r sine of theta naught plus alpha x. So using v dv dx, that equals A of x. V dv equals 2/3 g sine of theta naught plus alpha x, that quantity dx. So if we integrate from 0 to x, 1/2 v squared is going to equal 2/3 g times this integral from 0 to x sine of theta naught plus alpha s ds. So v squared of x equals 4g over 3 alpha bracket cosine theta naught minus cosine of theta naught plus alpha x. And here, curved path is going to need curvature subtripetal form. And technically, this is going to be an approximation for our normal force here. N equals mg cosine of theta naught plus alpha x. And this assumes the incline changes slowly enough that local slope dynamics will apply. Okay, so that is number 11. Moving along now to number 12. So two masses are connected on 3 springs. Determine the equations of motion, the normal coordinates, the normal frequencies, the mode shapes, and the physical interpretation. Okay, so this is a coupled oscillators problem, and at 2 equal masses m, 3 springs of constant k with walls on both ends. Wall spring, mass spring, wall. Let x sub 1 x sub 2 be displacements from equilibrium, and for mass 1, m, x sub 1 double dot equals negative k x sub 1 minus k times the quantity x sub 1 minus x sub 2. M x sub 1 double dot equals negative 2k sub 1 plus k x sub 2. So for mass 2 here, mx sub 2 double dot equals negative k x sub 2 minus k times the quantity x sub 2 minus x sub 1. M x sub 2 double dot equals k x sub 1 minus 2 x sub 2 minus 2k x sub 2. So our matrix is m times this column here, x sub 1 double dot, x sub 2 double dot, and that's going to equal negative k times this matrix. This is first row 2, negative 1, second row negative 1, 2, and times this column x sub 1, x sub 2. So what we're going to do here, we'll try a equals e to the I omega t, then k over m times this matrix 2, negative 1, negative 1, 2, times a equals omega squared a. So our eigenvalues are going to come out to, when we solve, lambda sub 1 is 1, lambda sub 2 is 3. So omega sub 1 equals the square root of k over m, and omega sub 2 equals the square root of 3k over m. And our mode shapes here are going to be a sub 1 is proportional to this column 1, 1, and a sub 2 is proportional to this column 1, negative 1. So that's number 12. Moving along to number 13. So particle moves on the surface here, z equals ax squared plus by squared. Using generalized coordinates, derive the Lagrangian, derive the Euler-Lagrange equations, and identify conserved quantities. So Lagrangian mechanics problem. So our constraint z equals ax squared plus by squared. We're going to use generalized xy. So then z dot is 2ax x dot plus 2by y dot. Our kinetic energy, T equals 1/2 m times the quantity x dot squared plus y dot squared plus z dot squared. In our capital T here, that equals 1/2 m bracket x dot squared plus y dot squared plus the quantity 2ax x dot plus 2by y dot, that quantity squared, close bracket. So our potential energy is going to be V equals mg times the quantity ax squared plus by squared. Our Lagrangian L is equal to 1/2 m bracket x dot squared plus y dot squared plus the quantity 2ax x dot plus 2by y dot, that quantity squared, close bracket, minus mg times the quantity ax squared plus by squared. Our Euler-Lagrange equations are going to be ddt, partial derivative of L with respect to x dot, minus partial derivative of L with respect to x equals 0, and ddt, partial derivative of L with respect to y dot minus partial derivative of L with respect to y, that equals 0. And since L has no explicit time dependence, E equals T plus V is conserved. And for a generic, A cannot equal. There's no continuous rotational symmetry, so no angular momentum conservation. And if A equals B, axial angular momentum is conserved. Okay, so that's all for part 4. Thank you very much and have a great day.